This is the video lesson for 11/3/2016. For any students that may have missed it, I'm going to go back and quickly go through how to use Boyle's law to calculate volume or pressure changes at a constant temperature, or use Charles's law to look at the relationship between the volume temperature as held at a constant pressure and those changes, or Lussac to calculate pressure temperature changes. Then we will also look at using combined gas law to calculate volume, temperature, and pressure at the same time, and when we're looking at those. Just a special note, ultimately the goal is to be able to apply combined gas law to any of the three above: Boyle's, Charles, or Lussac. We will also quickly look at Avogadro's contribution to volume, volume of a gas at standard temperature pressure in relation to 1 mole. So the opening question today is how will a change in energy of molecules in a gas, how will the change in energy of the molecules in a gas be measured? Specifically, what happens if we increase energy or decrease energy? So basically what I'm looking for, or what we should have come up with, is that any change in energy is going to affect the temperature. So if we increase the energy, we're going to increase the temperature. If we decrease the energy, we will decrease, or a decrease in temperature will show a decrease in energy. All right, so moving forward. So again, as I said before, we're going to be looking at Boyle's law, Charles' law, Lussac's law, and Avogadro's law, which is volume versus molar relationship. And we will go into those in more detail. I will show you one practice problem for each, and then you will be expected to be able to do these on your own. So some things to know. We are going to be dealing with 4 basic variables in this. We will be looking at volume, which will relate as V, pressure, P, temperature, T, and moles, which we'll represent by lowercase m. So as we progress through this unit, for the most part, I'm going to be looking at volume either in liters or milliliters. We need to be very careful and pay attention to what it is given in the problems. For Boyle's, Charles's, and Lussac, it's okay to have it either in liter or milliliter. It does not matter. For ideal gas law, we are only looking at liters. So make sure you always convert to liters in ideal gas law. Temperature, you will need to convert it to Kelvin. Remember, Kelvin is degrees Celsius plus 273. That's going to be the conversion that we need to account for. I want all answers in Kelvin all the time. And then for pressure, primarily I'm going to use atmospheres, but understand that kilopascal is also a unit that we will use. And then just if I've ever presented in anything else other than atmosphere or kilopascal, here are the conversions. 1 atmosphere is equal to 101.325 kilopascals, or 101.33 kilopascals. 1 atmosphere is equal to 101,325 pascals, because remember that 1 pascal is equal to sorry, 1 kilopascal is equal to 1,000 pascals. Um, and then the other units that we will use, um, that you may see in some of the problems, is it will either be written in torr or millimeters Hg. Essentially, these two measurements are the same thing, and these are the pressures that we get from a barometer, like the one in my classroom, where we'll see it in millimeters of mercury. And the conversion for that is 1 atmosphere is equal to 760 millimeters of mercury. So moving on, Boyle's law. Big thing I want you to know about Boyle's law. Boyle's law holds temperature constant, so temperature does not change. So we are only looking at the relationship between volume and pressure, and in order for this one to work, we are looking at a flexible container. So this, in some way, we have to be able to manipulate the volume of this container. Either it's a rigid container with some sort of plunger that we can reduce the volume or expand the volume, or it's something like a balloon, or has sides that we can squeeze or compress. So the relationship that we are looking at in this, it is an inverse relationship, because as we see, as volume increases, pressure will decrease. Or if we increase pressure, volume will decrease. So we look at it in the relationship, numeric relationship or equation relationship, as to P1 times V1, our initial pressure times initial volume, will equal the new pressure times the new volume. If we were to graph volume versus pressure in a Boyle's law relationship, it's going to make this curve that we see, volume versus pressure. So we'll see this trend as an inverse relationship. So let's look at how to work one of these problems. So real quickly, if we are looking at Boyle's law, let's look at this relationship firstly. So the way I approach any of these problems, the big idea, or the big thing that we need to do, anytime we look at one of these problems, we need to go ahead and pull out what is our units and what are our givens versus what are we looking for. So question number 1. A sample of oxygen gas occupies a volume of 250 milliliters at 740 torr pressure. What volume will it occupy at 800 torr? So since we are only dealing with pressure and volume, and since both of our pressures are represented in the same units, we don't need to do any kind of conversion here or anything like that. I do personally prefer atmosphere. It's just a cleaner number, but we can leave it in torr for this. So let's go ahead and pull out our givens. So we have 250 milliliters, so we're going to call that V1. 250 milliliters. And then we also have our pressure 1, which is 740 torr. V2, we want to know what volume. So this is our unknown, this is our question mark. And just to kind of think about it, if our volume is measured in milliliters here, what should we expect our new volume to be measured in? Milliliters as well. And then we can also look at our P2 is going to be 800 torr. So that's our new pressure. So when we're looking at this, in some way we were able to increase the internal pressure of our system. So just looking at this relationship, it's an inverse relationship. So if we increase the pressure, what does that mean that we had to do to the volume? So our expected answer should be a lower volume, because as pressure increases, volume should decrease. So setting this up in our equation, P1 is 740 torr times 250 milliliters equals 800 torr times our new volume. So just looking at this problem, setting it up, if I divide both sides by 800 torr, it cancels it out over here. So essentially we have 740 times 250 divided by 800. Now just working through it before we do everything, I want to show you why you get your units in milliliters. So we have torr divided by torr, so that cancels, leaving only milliliters for your solution. And then let's work so when working the problem, a couple of things to notice. All of our units are in 3 sig figs because we have a decimal point after the end of each one, so we have 3. So when we report our answer, when we put it in the calculator, or when we multiply it out, we should get something like 234.375, but since we can only put it in 3 sig figs, our answer is 234. Now, the question that I have in looking at this relationship, I said earlier that we should have expected a decrease in volume. So we started off with 250 milliliters and we end up with 234, and yes, that shows a decrease in overall volume. So go ahead, you have this worksheet, you should be able to work the remaining 7 on your own. Please pay attention to units, please pay attention to what units will cancel as you do this. Alright, so that brings us now to Charles's law. Charles's law holds pressure constant, so that means that pressure does not change. So when we're looking at these, we are only looking at the relationship between volume and temperature. And so this one is a direct relationship. So if it's a direct relationship, if we increase the volume, what should we expect for pressure to do? We should expect an increase in pressure as well. So looking at this in the equation form, what that tells us is that we have initial volume divided by initial temperature equals new volume divided by new temperature. So just kind of looking at that with numbers, let's just pretend that we had a volume of 1 milliliter over a temperature of 2 Kelvin. When we set this up proportionally, that means that if we increase the volume, if we double the volume to 2 milliliters, then what should that do? What should we expect to happen to the temperature? We should expect an increase in temperature, and it should increase by a factor of 2 as well. So that means that we go from 2K to 4K. Now, looking at this, do you see that 1 milliliter over 2 Kelvin is equivalent to 2 milliliters over 4K? Both of them would come out to a constant of 0.5. So yes, we have a direct relationship. Volume increases, temperature increases at the same proportion. If we look at this as a graph, it's going to be a linear graph with an equivalent slope all the way up. And just so this particular slope would be 1 over 2. All right, as we're moving up. All right, so looking at an example of how to work a Charles's law, um, we can set this relationship up as V1 over T1 equals V2 over T2, or we can put it in a relationship like this: volume, initial volume times new temperature equals new volume times initial temperature. Important thing to remember when doing problems dealing with temperature and gas laws. Always convert Celsius to Kelvin. So always convert to Kelvin. So looking at this sample problem, let's do number 1 again. So let's go ahead, just like we did on Boyle's law, we're going to pick out our givens. So we need to know, looking at this one, we need to know V1, V2, T1, and T2. And one of the things that I'll say is go ahead, get in the habit of writing your givens down. Either identify them in the problem itself or write them out to the side. So a sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? So first thing I see is that I have my temperatures in degrees Celsius. So let's go ahead, convert those to Kelvin by adding 273 to each one. And get our units there. All right, so when we do our conversions, we see that we really have 298K. That is our T1, because that's the first temperature that we're given. So we have 298 Kelvin, and then our final temperature is 368 Kelvin. All right, so looking back at the problem, I need to find my initial volume. My beginning volume is 250 milliliters. And my new volume is our unknown. Now, our initial volume is in milliliters, so what should I expect my new volume to be in? Milliliters as well. And if we look, we see that our temperature does what? It increases. So what should I expect my volume to be? Again, this is a direct relationship, so I should expect to see an increase in volume. So if my temperature goes up, I should see a increase in volume as well. So setting this up, I'm going to use this setup just because I like it a little bit better. So let's go ahead, plug in our information. So volume 1 is 250 milliliters times temperature 2, which is 368 Kelvin. And in my relationship, that is equal to my new volume, V2, which is my unknown, times 298 Kelvin. Now, the reason why I like this setup a little bit better is it's just a little easier to manipulate. So if I divide both sides by 298, that cancels there. So that gives me 298. And just looking at unit cancellation, Kelvin divided by Kelvin cancels. leaving us with milliliters in our answer. And now let's go ahead and solve. So when we solve this, we see that we get a number like 308.72. If we go back to our problem, we have 2 sig figs here, 2 sig figs here, 2 sig figs here. So my answer that I expect in this one should be an answer with 2 sig figs. So I have 308. I'm going to report that as 310 milliliters because 8 will round up to 1, and now I have my 2 sig figs. Any questions, comments, or concerns? Let's move forward. Lussac holds volume at constant, so remember, volume doesn't change. And then, so now we look at a relationship between pressure and temperature. Again, Lussac, like Charles, is a direct relationship. So that means if pressure increases, we should see volume increase as well. As one goes up, the other goes up. So again, just like before, looking at this numerically, if I had a 1 to 2 relationship here and I triple it, so if I go up to a new pressure, well, let me correct something, back up, not volume, temperature. So as pressure increases, temperature increases. Sorry. So when we're looking at this numeric relationship, if I increase the pressure by a factor of 3, then my temperature should also increase by a factor of 3. So that would make our new temperature 6, whatever units. All right. So we get the same type of graph in this one as we had before. When we look at pressure versus temperature, we see this linear increase at the same slope. However, whatever our slope is going to be. All right, so let's look at one of these as a problem. Work this together. Again, since we're dealing with temperature, remember to convert to Kelvin. Always convert to Kelvin. So I'm going to go ahead and do this in this problem before we even start it. 100 degrees Celsius, so that would be 373 Kelvin. 300 degrees Celsius, that's going to be 573 Kelvin. So a sample of gas in a closed container at a temperature of 100 degrees Celsius and 3 atmospheres is heated to 300 degrees Celsius. What is the pressure? So just like I said before, somewhere on your paper, somewhere on the side, let's go ahead and see what we have as our given. So we're looking for P1, we're looking for T1, we're looking for P2, and T2. All right, so reading through it, our first temperature is 373 Kelvin. Our first pressure is 3.0 atmospheres. Our new pressure is our unknown, because we have what is the pressure, and our new temperature is 573 Kelvin. So let's go ahead and plug it into the equation, and like I did before, we can also write this as T1 times T2 equals P2 times T1. This says the same thing as this. It's just easier to manipulate it in this format. So I'm going to go ahead and write out my equations, plugging in my numbers. So I have 3.0 atm times T2, 573 Kelvin, is equal to P2 times temperature 1, which is 373 Kelvin. Alright, again, if I divide both sides by 373, that cancels. And now I put all of my numbers on the same side, isolating my unknown. 373 Kelvin, and we see that we have Kelvin divided by Kelvin, so that means that our answer is going to be in atmospheres. And I'm going to write my answer over here in the box just so that you can cleanly see it. So let's go ahead and do the work. Alright, so when we calculate this out, we should have gotten something to the extent of 4.60857. Looking back in our problem, we have 4 sig figs for the temperature, we have 2 sig figs for the pressure, so we're going to go by the lowest number of significant figures, which is 2, so we will report our answer in 2 significant figures. So looking back at our solution, it would be 4.6 atmospheres. Now, just to go ahead and make sure that we follow through with what I've been showing you with the relationship before, we said that this relationship is direct. Can't spell today, D-I-R-E-C-T. So looking at this, we have a increase in temperature, so we should see an increase in pressure. So looking here, we went from 3.0 to 4.6, so yes, that follows the rule that we saw an increase in pressure as well. Now, let's move to combined gas law. Well, first, let's just go ahead. I'm going to go ahead and give you some mnemonics to remember this. So Boyle's law, we take the B and the L, and Boyle's law, in Boyle's law, temperature is held constant. So we take the B, the L, and the T. And so a way to remember Boyle's law is think BLT. Boyle's law, temperature is constant. For Charles's law, pressure is constant, so we'll just take the C and the P, think cheese pizza for Charles's law. If this kind of thing helps you, it might help you remember it. For me, it's easier just for me to remember the relationships. Lussac, G and V. Volume is constant, so green veggies will help you remember Lussac. And you could even say green leafy veggies, and incorporate the L in there. I did do that when I was younger. Alright, so last one of the day, and this one, what I want you to understand about combined gas laws, any of the 3 types of questions that you were asked before, whether it be for Boyle's law, Charles's law, or Lussac, we can actually apply combined gas law in any of these, because if we were to hold temperature constant, then you can see that we essentially have Boyle's law, P1 times V1 equals P2 times V2. If we were to hold pressure constant, you have V1 over T1 equals V2 over T2. if we hold volume, which is Charles's law. If we hold volume constant, then we have P1 over T1 equals P2 over T2, which is E. Lussac's law. So this combined gas law, all it does is incorporate all three of those into one. Again, make sure you remember always convert to Kelvin. There's just some problems that occur if we leave it in Celsius. Even though the change is the same, when we're dealing with Celsius, we can end up with negative numbers, and we don't want to have to look at it in that way. We want to always look at it in a positive number. So let's work an example of a problem of this one. All right. So on your practice sheet, we have our combined gas law. And another way to look at this relationship, again, I just remember I like to simplify it. So we can take P1 V1 times T2 is equal to P2 V2 times T1. Again, that's just from manipulating the equation. This is one of those things that helps me. I struggle in math and manipulation sometimes, so it helps me to look at it in this relationship. All right, so again, let's look at problem 1, and we will go ahead and solve it. So a sample of nitrogen monoxide has a volume of 3 liters at a temperature of 20 degrees Celsius and a pressure of 1.5 atmospheres. What volume will the sample occupy at 30 degrees Celsius and 2.5 atmospheres? So let's go ahead, isolate our givens. So we have a P1, V1, T1, P2, V2, T2. So we want to know what's our unknown, what's our givens. Go ahead and pull those out. So we have 3.0 liters. That is our V1. So we're going to write that right here, 3.0 liters. Temperature 1, we have it in Celsius here. So 20 plus 273 is 293. So our temperature 1 is 293 Kelvin. And then our pressure is 1.5 atmospheres, 1.5 atm. And then moving on, we want to know what volume. So that's our question. And now, just paying attention to units, my original volume was in liters, so I can expect my new volume to be in liters. We can verify that through unit cancellation. Now let's go ahead and pull out the rest of the information. So I can't see something, so let me erase this. Our temperature, our new temperature is 30 degrees Celsius, so that's going to be 303 Kelvin. If I did my math right, 273 plus 30 should be 303. And then, so that we're going to write 303 K. And then our new pressure is 2.5 atm. 2.5 atmospheres. So let's go ahead and do our work. So let me go ahead, just to make things nice and neat. I'll make my answer box right there. I'll do my work over here. So let's go ahead and plug it in. P1, 1.5 atmospheres times volume 1, 3.0 liters. And I'm this format times my new temperature, which is 303 K, equals pressure 2.5 atmospheres, times V2, which is our unknown, times 30. Now, catch me. My T1, which was 293 Kelvin. All right, so if we divide both sides by 2.5 and 293, that cancels that out, putting our relationship like this. So we would have 2.5 ATM times 293 Kelvin. Now, one of the things that I'm expecting you, as you're in chemistry, you understand the algebra of what I did, just manipulating the equation. So you should be able to keep up with that part. All I'm asking you to do is solve for the new volume, which should be in liters, and just proof of that. Kelvin cancels Kelvin, atmospheres cancels atmospheres. All you're left with in units is in liters. So go ahead and solve in your calculators and then check your answer. All right, so as with any of our problems in chemistry, we always need to make sure that we are following significant figure rules. So looking at our volume, we have 2 sig figs here. Temperature, technically we only have 1 sig fig here, but I'm going to go ahead and count that as 2, just because most thermometers are accurate to the one's place, even beyond, and I will say that we have 2 sig figs everywhere else. So we'll report this answer in 2 sig figs. So looking at my calculations, I came out to 1.8614 when I calculated it. So reporting this in 2 sig figs, we would say that we have 1.9 liters. And just going through again, make sure you pay attention to the units it's supposed to be in. Make sure you pay attention to converting to Kelvin. If you did not convert this one to Kelvin, you would not come up with this answer. I haven't mathematically verified that, but I know that you run into some problems when you don't convert Celsius to Kelvin. There are times that you won't come up with the same thing. So hopefully this will help you out if you get stuck. Please remember to watch these videos. The test for this unit will be on Monday. So take care.